Okay, so I've tried to give some notes back. Some of them are specific to you, but there's a couple of notes I think I wrote to everyone. One of them was explain the problem in the beginning. Let me explain what I'm trying to just tell you there. So what I'm looking for is you come up here and you say, I'm doing the register file, and you go on. Well, okay, great, you're doing the register file, but why is the register file important? What purpose does it show or use, or why are we trying to implement it? So, for example, if you're doing the register file, you might have a picture of this diagram up here of the full processor and say the register file is where we're going to store all the temporary information, so later on we can operate on it and then do any type of meaningful work with what's being stored. ALU, you would say this is the part that actually does the work, the actual addition or NANDs. Memory, where we need to store anything that cannot be stored within the register file so we can write to it. And then what was the other ones we had?
MUX to control data flow.
Oh yeah, MUX control data flow through our processor, because look, we need to have a MUX to figure out what's being sent to the register file, what's being sent to the ALU. The decoder, which is part of the control ROM, so we know which line to activate the different wires that are coming up and controlling each piece of memory. So the first part of explain the problem is we have the problem with a single processor. We got an idea of that, but explain why your piece is important inside of it is what I was trying to get at. I think the other one was a lot of people were trying to read the code as opposed to explain what you're testing for. We trust your test code works, believe it or not. We just want to know what it is you're testing for. So if you could test every single output like with a MUX, you just say I tested every single possible combination because it was possible to do that. And that'd be pretty much your summary of your test cases, and that would have been it. Same thing with your decoder. The register file would probably be a little more complicated because you want to be testing that you can read, but you want to test that you can write at the same time. When you wrote something there, you can read it later. That'd probably be pretty good right there. ALU, then test the NAND real quick. With the adder, you probably want to test overflow as well as just simple additions as well. And instruction memory, same thing with register file. You can write to memory and you can read from it. Okay. Everyone good? Mm-hmm. All right, so hopefully you have a clearer picture of what's going on with the single cycle processor, because now your next lab, I'm going to go ahead and assign it today, but you're not going to have everything to get started right now. So let me jump over to... Yes, PJ? Hmm? PJ? Wow. As you can see, I haven't committed all of this. If you were to look on GitHub. Oh, it's going to be good. All right, now that you have hopefully all the components, we don't quite have all of them, but I'll get them all together for you in the coming days, hopefully by the end of this week. You're going to have all your different components. The job of this lab is to actually piece them all together and make a functioning processor.
So you're going to give us all of the actual stuff.
Right. Yeah, and you're not going to rely on other people's code. You're going to have my actual code where I've tested it and it worked. Well,
My code is reliable.
well, I've tested it to have it work with every other piece that I've tested. Because just because your works, maybe your specification wasn't the same as this guy's over here, right?
I have a name.
I know David.
Yeah, David.
How you know I wasn't pointing to PJ? All right. First off, all your code must be in the Lab 5 directory.
Wow.
Follow. You would be surprised how often people have problems with that. Note number 2, follow the class slides to make your processor. You're going to look in the book. The book is going to have something similar to this, but it is not going to be the exact same. This is what you're working off of, okay? Yeah, and open up the presentation, because if you recall, the presentation would go through different ads, what it's supposed to look like, what are the bits supposed to be that are being passed along, and that'll be greatly, very, very helpful, for writing your processor or creating it.
That's the slide in which you were talking off to the side. And there was no
Oh, nothing that would help.
no pointer or whatever. You were writing things off
Oh,
the
writing
side.
numbers and...
I like how this number just disappeared right here.
Yep, it was
Didn't need it.
This is a 0. You know how this one's a 0? Select the top one. Obviously, I need a 0 right here to forward it along. So, let me write that. Note to self, fix slides.
Isn't that always a note to self?
Yeah, this is getting really bad with the slides.
It's fine.
And then your answer to us is, oh, we've noticed something wrong. He says, oh, I just fixed the slides.
All right. Okay. So that's what we're going to do. Setup in part 1, I highly recommend you set up your instruction memory such that it will load your program during reset. Ooh, what is reset?
What is that?
Oh, we never talked about it. We have not talked.
So every processor has a very special layer on top. That's the reset layer. And what it does is it sends reset to basically every component that has memory on your processor. And that's supposed to set it to 0. So for example, when you send reset to the register file, it makes everything 0. Memory, it makes everything 0. PC, 0 as well. That way, after you hold the reset line, once the first instruction is going to be fetched, the PC counter 0, the very first one that you load in. So that's what's the reset line. And let me see.
Resets everything.
It resets everything. Whoa. All right. Let's see if I can
I already have part
give
0
you.
done.
What's that?
I said I already have part 0 done.
Yeah.
All right. So here's probably the register file I'm going to give you. Notice here at read 1, read 2, where it's writing to, the data, it's enabled out 1, out 2, which corresponds to read 1, read 2, the clock, and then the reset. I think actually if we go through this code, it'll help you the most.
Why do you have a 5-bit read mode? Just 'cause. Oh, 4 plus 1, 5. Oh, I see. I read it. My, don't worry what.
No, actually, you're right. It should only be about 3 bits here.
We wanted an explanation for the comment.
Let's say, I didn't
Okay, great. Right, okay, so then write data to be written to. Are we enabling the write? We have a clock and a reset. These are all input wires. Output wires, out 1, out 2. Here's our register file. Hey, look, our register file is 32 32-bit registers because we're implementing MIPS.
When you want me to change it, can I just do that?
Yes.
Make it 32?
Sure, why not?
Fantastic.
So basically.
Wait, I'm recording this. I'm giving you the code. Man.
Thank you.
Man, right.
I'm literally just going to copy everything you have now. But I'll say I looked it up. So.
He'll give you credit.
Just-
I've already cited you in my
Yeah.
sources page.
All right. So this is the data flow model where we assign out 1 to just be whichever register we're reading from. Everyone good?
Sure.
Forget the pause clock right now. Here's the reset line. Notice that at positive edge of reset, when you hold reset high, we make everything in the register file 0.
No, okay. I saw
Wow.
that, but didn't know what that meant. Sorry.
Huh. How about that?
Huh.
Dr. Russ has been riveting, but I got ahead of stats, so
Bye.
Good luck.
thank you.
I've
Class
only did that
sucks,
before.
so-
Wow.
I don't like stats.
Oh,
That's
class.
all
Oh,
video.
I thought you were talking about this class.
No.
All right, notice that on the positive edge of the clock is when the write actually occurs to the register file. And then notice I have code right here that's going to display the register file every single clock cycle. So on the positive edge of the clock, it writes to it and then displays all the information or all the contents of the register file in hex.
But you have it only writes if the write enable is.
If write enable, go ahead and write the data there.
And that's on the always.
That's always on the positive edge of the clock. So whenever the clock goes up, it's
It
going to
checks to see if it's, write
enable,
enabled.
and if it is, they'll take the write data and store it into wherever the register file needs to be.
And that it guarantees that you're only writing on the positive edge.
Correct. The write is committed on the positive edge of the clock. Yeah. All right, where were we? Okay. We got. How do we set up reading? I haven't submitted this yet because I'm still waiting to get all your feedback. We want the test case, don't we? TV, there we go. Or it's not even in there. Beautiful.
Yay.
Did GVim go away? No, okay, good. Tab new. That's gonna be the instruction mem. All right,
Hey, my stuff.
your stuff. So,
An address.
hey, look at this. Clock and reset, input and address, output and instruction. This is instruction memory. It's going to be a lot simpler than data memory. Hey, look at my memory. 30, okay, this time, I guess you do need to write it this way. The size of each element and how many elements there are. Well done, sir. Well done. On the positive edge
That's
of
the individual size of the element.
yeah, so this is the individual size of the element, and this is how many elements there are. I had that backwards.
Yeah, why
Yes.
is it 0 and then
65,535. That's 64K. So on the positive edge of the clock or the positive edge of reset, which whenever one of those goes positive, if the reset line is on, put in a no op, and this is how you would read memh from program.bin. We haven't talked about that because you're going to write in this. I have an assembler. You're not going to write the assembler. I've written the assembler. You can write the instructions. You hit go, and it'll assemble it so that this can read your program and store it into memory.
sure.
And then on whenever the address changes, or the negative edge of reset, you if the reset's 0, go ahead and read the next instruction in, and then I have a little printf saying, moving instruction, whatever this is, to the memory. Right. Sounds great. You got this, Sydney? This has been done for you, so you don't have to do this anymore. What you should hook up first is incrementing the PC counter so the CPU will halt when it reads the halt instruction. If we were to go back and let me go ahead and look up the MIPS, that guy. Right now, all it does is hold reset, turn on reset, initialize the clock. Notice up here I have the clock ticking every cycle. We're probably going to want to change that when we add gate delays from one to something else. Wait 10 ticks just to make sure reset did it. Release the reset line. And this is where you would start beginning your simulation. Right now I just have it going 100 ticks and then finish so it ends. You need to actually implement once the halt instruction has been read to stop your simulation. All right.
Being under an always or something. Let's see.
Always, that means always execute this at every tick, make the clock equal to not the clock. So it's,
It toggles.
yeah, it goes from 0 to 1, just like a clock.
I have a
But
problem.
shutting it down right now.
Whoa!
So we would go, instead of that pound 100 ticks or whatever, we'd have like if halts finish.
Somewhere.
Somewhere. Great.
Probably not in here. Most of the time, these are the two things you're going to be changing. One is what you need that clock to be, because remember, based on your gate delay is how long that clock needs to, how wide that clock needs to be, right? Because your gate delays are going to determine your clock rate.
Oh, you wouldn't have it
200.
always, is what you're saying. It wouldn't be-
Well, the gate delays, if you had no gate delays, then this is perfectly fine because everything happens instantaneously. But that's not true
Right.
in real life. So once the gate delays are added, one of the things you're going to be changing is how do you adjust this clock to actually account for it. Naturally, you can cheat and just make it 1 million,
Yeah.
but you probably won't get it. You know, you may want to do that first, but you're not going to get a good grade.
Wait, now, the longest, yeah, so we want the longest gate delay, but do we want the longest gate delay in the whole,
And the whole processor.
process?
Hmm.
So basically, the longest,
Yeah,
if
draw
if the ALU by some chance happens to have the longest gate delay, then whatever that gate delay is.
Well,
there.
plus everything around it, right?
Also, we're gonna include, so everything.
Everything.
Didn't we just go through this?
The longest path.
Can we just go through this? You know, yeah, right here.
Yeah, right there.
Let's do it again.
Oh, right.
Look, see how I did a quick gate delay estimation here? Your numbers are going to be different than what is presented up here on the board.
Dang.
But, okay,
How
so the
different?
monks,
How different?
Somewhere between somewhat and very.
Ah. Got
for
it.
those gate delays, we went through with the gate delays, I didn't really understand at the time, now I better, but the initial mux and PC, you didn't have that in there.
Yeah.
But that would have at the very beginning. Oh, wait, we start for the program count, never mind.
Yeah, we start from the PC counter.
Yeah.
And it's assumed that going PC plus 1 back to the PC does not take more than the rest of this, which is actually a fair assumption.
Awesome.
Okay, so yeah, you probably, the only thing in here you'll be changing is what your clock is, and then removing this final finish line once you get PC plus 1 working and you get a halt instruction moving through. Let's see, up here, I have set up this processor. It's a MIPS 32-bit. It has a clock and a reset. That's really all a processor has. A clock going into it and a reset. I have your PC counter and 1, which stores the value 1. I have put in a bunch of wires.
Stores the value one.
You know, you may use these or not. It is completely up to you.
Oh, great.
Assign next PC is always PC plus 1, PC inputs next PC. The reason for that is so that you can update PC to be PC plus 1. I've gotten that started for you. Hopefully you'll be able to work there. Notice on reset I have the PC equal to 0 and 1 equal to 1. And if we're not on reset and we have the positive edge of the clock, I'm displaying what the PC is, what 1 is, what the next PC is. You probably want to fix that. What the instruction is, decode out from the ALU, sign extend, and the some instruction bits. Naturally, you may fix this all you want. And then be the PC equals PC input from the MUX. I have not written anything else. What I expect is right here, you're going to have a lot of code. Well, actually, you're really going to have, if you know what you're doing, you're only going to have about 15 lines here where you
know what you're doing.
You'll have of just each module that you are instantiating and hooking up.
Oh, so we're just instantiating the model in there.
And hooking them up correctly. That's really all you'd have to do.
Hook up the models correctly.
Because everything else should be coded correctly. You just need to put everything in here correctly to make it work.
No,
Oh, so we're only
there were one or two
changing-
modules where you said we had to adjust the, like the calendar, the module, we'll have to
So we're
adjust
only
those
changing
finishes.
those 2 files.
When done correctly, those are the only 2 that you have to change.
Okay.
Yeah, it's the first hurdle with this project is understanding what's going on. That's why I'm explaining it now, and I'll explain it again next class.
So we're gonna have to do a whole bunch of crazy stuff. No, we just gotta figure
No, you
out
just
how
did
it-
the crazy stuff. You just have to figure out how any of this
How it
makes
fits.
sense.
Yeah.
But now I need to get everyone's data together and massage it so it makes some sense.
Yeah.
Here's a quick, I did this as well. Once instruction is equal to the halt instruction, I have it display halt instruction encounter in simulation finish. So really, I got that going for you. You just got to hook up the PC correctly, instruction memory correctly, and then you should eventually get to a halt instruction. And then after that, just start piecing things together.
Sewing it up.
Sewing it up. All right, so part 2, decide the order of instructions you want to implement. I just mentioned that, but here it is in here. It's best to start with the basic, then build up to more complex. So first, implement the halt instruction. Actually, I've implemented that for you, but you need to implement the PC equals PC plus 1 in order to get to the halt instruction as well as the instruction memory. Load, so you can load values to the register file. Add, NOR, NOOP, swap, and branch of equal is what I would recommend. BEQ is going to be the hardest to because branching can be kind of weird. Make sure you write it in a test for each instruction. I highly recommend you write 1 test for each one of these. At least 1, I'm sorry. You probably want to write a couple more. And then you should be done. Yes, this is a bigger project. Now you have 2 part 2s. Make sure you do test some loops in complex programs. I have provided some of the programs directory. We will look at that briefly. I'm going to go over this again because I haven't talked about the assembler yet, which is fine. So prg.s. So here's an actual program. This should look familiar. Load 5 in the value -1. This is that you're decrementing 5 and then branching back up until it's done, and then you halt.
Yeah, we're definitely gonna need it.
All right, so I made a makefile, so it compiles it and runs it for you. Right now, it has a bunch of Z's and some other things that aren't too useful, probably because
It's not doing anything.
it's not doing anything yet. So I at least got this started.
That looks so weird.
It does look weird. I will go over this again next class because I haven't talked about the assembler yet, and y'all are probably tired.
Yep.
You got about 45 minutes of lab time. I know y'all have some homework, so I'll let y'all get to it. And I did assign this to be due March 19th, which is that 3 weeks?
March 32nd, you said.
32nd? Oh, man, that was definitely a Matt statement.
Today's the 19th,
Today's 19th?
and that's the 19th. So
Okay,
then we got 4
you got a
weeks.
whole month. Yes, but one of those weeks is spring break, so you have 3 weeks.
Yeah.
I mean, unless you want to count this as 4 weeks.
No.
I mean, technically it's 4
No,
months.
I don't think any of y'all are going to actually do this over spring break. Anyone?
No.
No. I'll turn my computer off.
You're not even going to turn it on?
I'm gonna play games.
Wow.
I'm not.
I just got a new controller for my computer, so
Controller.
yeah. I
Any
got an Xbox
questions?
controller.
We'll discuss this again next class, but I wanted to give you a quick preview of what's coming down.
We're gonna cry. We're gonna cry so much.
The hard part of this project is understanding what's going on.
Great.
Yay.
I wish you could.
That's encouraging.
Did you just hear the statement you just
Yes.
said?
Because the coding part is not that bad.
It's already done for me.
Okay.
Well, the hard part of the coding has been done for you.
That's slightly more encouraging.
Yeah, the hard part of the coding's been done for you. What the hard part is understanding how this is all piecing together
Okay.
and how do
We're
you
gonna
put.
draw some diagrams.
That's a great idea. Draw diagrams and whatnot. We'll again discuss it on
Color
Wednesday.
code it.
Any other questions?
Can you help us with